The dot product is one of the most important operations in all of math. It measures how much two vectors are pointing in the same direction. If the two vectors have similar direction, their dot product is big. If the two vectors don't have similar direction, their dot product is small. However, this nice geometric picture only works in finite dimensions, and only over the real numbers, or the rational numbers. But it turns out that dot products also make sense in complex vector spaces, and in infinite dimensions. In quantum mechanics, this notation is common. This is called the bra, and this is called the ket. But bras and kets are just vectors, and this is just their dot product. In computer graphics, you use dot products to do photorealistic renders, since the amount of light an object receives depends on the direction of light. In calculus, you use dot products to compute line integrals of vector fields, since the line integral depends on the direction of the tangent vector. And again, in quantum mechanics, dot products are used to compute probability amplitudes, which are used to see how likely a quantum mechanical system is to collapse to a particular state. And these are just small examples in a handful of areas. Bottom line, without dot products, you can't do much quantum mechanics, or computer graphics, or calculus. Today, we'll try to visualize dot products from scratch using the OpenGL Shading Language. And yes, we'll be using dot products to visualize dot products. The first thing that we want to do in order to draw an arrow is to draw a line. So let's write some routines. Let's write a routine in order to do just that. And the way we're going to draw a line in a fragment shader is by taking the coordinates of each pixel and coloring that pixel according to how close or how far away it is from the line. So that functionality is going to be provided precisely by this function. And what we are writing right here is a fragment shader. I barely understand what fragment shaders do, but I think they are supposed to be programs that run once for each pixel. And each time the program runs, it takes the coordinates of each pixel on the screen. And those coordinates are contained in this value here, frag coord. The values of those coordinates depend on the resolution of the viewport. So since I'm running at 1920 by 1080, the values for my pixel coordinates will go from 0, 0 on the bottom left corner to 1920 1080 on the upper right corner. So this line takes those coordinate values and normalizes them to the -1, 1 interval. However, only the values in the y direction will actually go from -1 to 1. The values in the x direction will also go from -1 to 1, except for the fact that the screen is not square. So the values in the x direction will go from something like -1.8 to 1.8, approximately, I think. Now, in order to compute the distance from each pixel to the line we want to draw, we take two functions. One called vector projection, taking two vectors. Vector projection scalar, which takes two vectors and returns a scalar. And the second one we are going to call vector projection, and it's going to take two vectors and return a vector, which will be the vector projection of vector A to vector B. And it will express this vector as a scalar multiple of vector B. We will be projecting vector A to vector B. And this scalar multiple here is precisely the scalar that this function above, this function here, vector projection scalar, is intended to produce. It is, and it turns out, and it is in my opinion almost a miracle, that that scalar can be computed as a quotient of dot products. So we take the dot product of vector A with vector B divided by the dot product of vector B with itself. And then, using these two routines, we can find the distance from each normalized pixel coordinate to the line by taking the distance of some vector x to the vector projection of some vector x to some vector y. And we will specify right now what those two vectors are. The first one, vector x, will be the vector that goes from A to our current pixel. And the second vector, vector y, will be the vector that goes from vector A to vector B. Vector AP comes here, vector AP, and then vector AB. And assuming we haven't done some horrible mistake, we should have something that looks remotely like a line. And let's say that we want to start by drawing a line that goes from 0, 0 to 0, 1. So another thing that we did in this first line here by normalizing our pixel coordinates is that we displaced the origin from the bottom left corner to the middle of the screen. So now our 0, 0 point is in the middle of the screen, and our point 1, 1 is somewhere around here. And each pixel currently is being colored according to its distance from the line that passes through the point 0, 0 to the point 1, 1. And large values correspond to white, and low values correspond to black. However, as it stands now, the line is too spread out across space. So probably the first thing that we want to do is squish the line in smooth fashion, so that it looks a bit better. And in order to do that, we can use the smooth step built-in GLSL function, which takes an anti-aliasing parameter. And for now, let's set our scale to 1, and we will use this variable here, scale, to zoom in or out as we want. So this smooth step function took that whole sea of distances, and it localized them in smooth fashion in the screen. But we want, well, or I prefer to have a black background, so we can invert those two values, and now our line looks like that. The second thing we want to do after we can draw a line is draw a line segment. And that line segment drawing function is going to use almost the exact same code as the other one, except that we're going to take this vector projection function and this vector projection scalar and clamp that vector projection scalar to the 0, 1 interval, so that now this vector projection is only going to be a scalar multiple of vector B, but that scalar multiple is going to vary from 0 to 1, and that should give us a line of finite length. So just to test if our function works, that does work. And now if we increase the scale to 2, our values in the y direction go from -2 to 2. So the origin, which is at 0, 0 here, is where our line segment starts. Remember that we specified a line that passes through 0, 0, 1, 1, and now the line segment goes from not just passes through 0, 0 to 1, 1, but actually goes from 0, 0 to 1, 1. So the point 0, 0 would be here, and the point 1, 1 would be here. And let us leave the scale as 2. Now that we can draw lines and line segments, we are probably ready to start drawing our axes. So this can start off by being the x-axis, and we can delay the application of our smooth squisher until later. And now our axes can be joined together by something which we will call upjoin. And this upjoin function is simply the straight up math min function. But I suppose it's nice to call it upjoin or something of sorts for semantic clarity. And since we are not going to have just a single object anymore, it's probably a good idea to start having a scene variable to compose all the objects in our scene. And that requires some background color. So the first value that the scene variable is going to take is the color of the background. And while we are at it, let's also define the color for the foreground. And also a gray value. And let's see if we can start mixing up the scene and have it actually work. So nope, that is not how we draw coordinate axes. When the x-axis goes from 0, 0 is a line that passes through 0, 0, and 1, 0, and the y-axis is done in this way. And then we want to squish them, of course. And now we are also going to draw a grid of lines at the integer positions. Nope, oh no. And that will use almost the exact same code. Nope, that's not the grid. Those are the axes. And this is the grid. And the grid of lines is going to use almost the exact same code as the axes, except that we are going to take our pixel coordinates and repeat them across space. So one of the ways in which you can repeat stuff across space is by using the mathmod function, and this is going to take a repeat value, which will be 1 since we want to draw grids or lines at the integer positions. And it so happens that we need a half repeat value here as well. And it's probably a good idea to define the repeat variables somewhere. So now we can call these things grid X, grid Y, and grid respectively. And again, assuming we haven't done something horrible, like forget to use our repeated coordinates, we will have a grid of lines on top of our axes. On top of our axes, like that. And if we take this grid repeat value, and so currently we're drawing a grid of lines at the integer positions, and remember we have a scale of 2, so on the in the y direction our values go from -2 to 2. But if we increase the grid repeat value, we are going to have a more sparse grid of lines, and if we decrease our repeat value, we are going to have a more dense grid of lines. Now, and this will correspond hopefully to the proper values in our coordinate system. So now that we can draw lines and line segments and grids, we can begin by drawing our first arrow. And the way we are going to draw arrows is by simply taking 3 line segments and sticking them together. So I'm just going to copy pasta some code that does precisely that. This is not compiling. for a bunch of reasons. One, because, one being because we need a rotation matrix, a 2D rotation matrix. And fun fact, this matrix here is not just a 2D rotation matrix, but it also happens to be the matrix representation of a complex number. Since complex multiplication rotates and scales complex numbers, and the complex numbers form a two-dimensional vector field over the reals, a two-dimensional vector space over the reals, we can use multiplication of complex numbers to rotate 2D vectors around. And the df-line segment O has a different signature, I think. So we need to add a thickness value here, which will come in handy to specify thickness for our lines. And our axes could have a thickness of this 0.1, and then our grid lines could have a thickness of 0.01. Let's see if this thickness is working. So let's say that this has a, super thick. Okay, so thickness is indeed working, apparently. So let's draw our first arrow 0, by using the arrow default constructor. Oh no. Okay, that's better. Arrow draw, and we will paint this arrow red. Oh, but we have no red, and also there's no function called that, so let's rename this to that, and let's define some more colors. RGB red, which is something like this, and then RGB blue, which is something like 0.51, and then we also want RGB purple, which I think has values like this. Arrow draw, we are forgetting to pass our pixel values, and there we have an arrow. So we will be finding the dot product of arrow 0 to arrow 1, and let's paint arrow 1 as a blue arrow, and changing their norms, their angles a little bit. So this arrow, let's say that this has angle of, 0.3 pi, and this has angle of 0.1 pi, and maybe we can change their norms as well. Norm, 0.5, and arrow 1 2.2, and we can specify these values here because the this code from here came with an arrow structure, which contains geometric information about the arrows, and in particular it contains a norm value and an angle value. The norm is also known as the length or the magnitude, and it is the length of the arrow, and the angle is used to specify the orientation of the arrow in two-dimensional space. And then this function here takes into consideration those things in order to draw the arrows. The nice, and this structure, this arrow struct here, could also be called a vector, but I kind of like calling it arrow, just to emphasize the geometric correspondence between vectors and arrows, at least for vectors, for finite dimensional vectors over the real numbers. And then the third arrow that we want to draw is the vector projection. And the dot product of two arrows, of the red arrow to the blue arrow, is going to be the product of norms, but not the product of the norms of the red arrow with the blue arrow, but the product of the norms of the norm of the vector projection of the red arrow to the blue arrow with the norm of the arrow we are projecting to. In this case, the blue arrow. Hopefully that was not too much of a mouthful. If not, I do apologize. And let's see if we can start drawing our second arrow. Let's paint this arrow white. And now, since we are computing the vector projection of the red arrow to the blue arrow, that vector projection by definition is going to be an arrow in the direction, or having the exact same angle as the arrow we are projecting to. In this case, arrow 1. And then the tricky part is the norm. And the norm of that vector projection is going to be given by the vector projection scalar. It's going to be given precisely, but by this formula which we implemented, which we wrote down here. So we need an analogous function for that takes into two arrows, in this case arrow 0 and arrow 1, and returns their and returns the vector projection scalar that we are interested in. But we're going to do all of this using the rectangular form of the arrows rather than the polar form. So we need a polar to rectangular function, which takes an arrow and returns its polar representation. And the way you compute that polar representation is by simply taking the norm of the arrow and multiplying it by the cosine of the angle of the arrow, and that gives us the x component of the rectangular representation, and then the y component is the norm of the arrow by the sine of the angle of the arrow. So now we take two vectors here, arrow 0 in rectangular form, which uses the function we just wrote. Oh my, nope. We were forgetting to specify our types. I think there's an extra mistake somewhere. And there is. Okay. And then we take another arrow 1 in rectangular representation, and now we apply the same formula as above, the quotient of the dot products that we use, and that gives us our desired scalar multiple. Now, for illustration purposes, I want to change this norm a bit. Wait a second. Okay. Oh yeah. Nope, that is still not right. Something's off. But I don't know what. Oh yeah, this is arrow 2, the norm of arrow 2. So this scalar multiple that we've returned here is not actually the norm of the vector projection, but a scalar that is used to modulate the norm of the vector we are projecting to get the norm of the actual vector projection. So that this scalar scales the norm of the arrow we are projecting to give us the norm that we were interested in all along. So now the white arrow is the vector projection of the red vector to the blue vector, or in the direction of the blue vector. And then the dot product of the red arrow with the blue arrow is going to be a scalar. However, what we are drawing here is something that is intended to look like a vector space. And the problem with vector spaces is that they are made of vectors. They are not made of scalars. So how do you visualize a scalar in the midst of a sea of vectors in a vector space? I don't know. I have no idea. So the first way that comes to mind of visualizing scalars in a vector space is by simply drawing a line segment whose length is intended to represent the value of a scalar. And let's see if that works. We take an arrow dot. We will have an arrow dot function which computes the dot product of two arrows. And that's simply the straight up dot product. And then we're going to draw a line segment. Let's say purple, whose length should, maybe, hopefully, help us visualize the value of the dot product, which is again a scalar and not a vector. So we want a line segment that goes from 0, 0 to dot product 0, and which has a thickness of 0.1. And then we should squish it, probably. Using the built-in smooth squisher. And now the length of this line segment should represent the precise value of the dot product of the red arrow with the blue arrow. And just as a sanity check, let's start doing this. So we are rotating the first arrow this arrow was too big, maybe 1.1. So as the red arrow rotates, both the vector projection of the red arrow to the blue arrow and the dot product of the red arrow with a blue arrow change. So two things are interesting. One is that when the two arrows are pointing in the same direction, where the direction of an arrow is given by a line that passes through the arrow. However, so the direction of an arrow is given by a line that passes through the arrow, and then we can have two orientations on the line. So when the two vectors have the same direction but positive orientation, the dot product, which is the length of this line segment here, takes large negative values. And then when the two arrows are pointing in the same direction and with the same orientation, the dot product takes large positive values. And then when the two vectors are orthogonal to each other, which means they are forming a 90-degree angle with each other, the dot product takes small values. And when they are perfectly orthogonal, they take a value of 0. So you can actually use the dot product being 0 as the definition of orthogonality. Hopefully that's a word. So that should do it. This is, I believe this concludes the tutorial, except that as a bonus, we can compute the dot product in an equivalent way, not using the rectangular representation of the two vectors, but using the straight up polar representation. So that should be the product of the norms times the cosine of the difference of their angles, which is this. And these two ways of computing the dot product should give us equivalent results. So there we have it. That concludes the tutorial. Thanks a lot for watching. This is my first tutorial, so please let me know all the things that I did wrong, maybe also the ones that you liked. And thanks a lot. Subscribe for more content, and thanks for watching.